What's going on, guys? My name is Johnny Bandon, and I'm your CCNA instructor for these CCNA video series. And in this CCNA video series, or this section, it's all about routing. So getting into how the Internet Protocol address version 4, version 6, right, transverses the World Wide Web. So going over what a router is, its role in the life of a packet, and then deep diving in to that router and how it makes those forwarding decisions and how it builds its routing table. So to kind of spell it out, guys, the first thing we're going to go over is one, the life of a packet. We're going to keep this simple, right? Because we know when we go to a web address, we have to query DNS, right? To do hostname and IP resolution. We have to choose the port, right? 443, 480, do the transfer of that data, TCP, three-way handshake, blah, 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 right? The true life of a packet is a lot deeper than we're about to go over. But again, we're just worried about IP right now. So we're worried about the IP header and how it gets from point A to point B. So we're going to go over the life of a packet. And then two, we're going to deep dive into routers and the routing table. Just a high level overview. And then we're going to get into routing protocols and how we build the routing table, right? We're going to go over how we build. And then we're going to end this section, we're going to end this section going over routing protocols. And the last thing we're going to cover is the 3 rules of how we determine how to forward traffic. So we're actually going to go over forwarding IP addresses. And this is, again, all in the perspective of an actual router, right? Because that's what we're talking about here, IP routing and the device, the router that makes IP routing happen. Let's go ahead and dive right into it. So the life of a packet. So if we take a look at our image here, we have this user sitting at PC1. He's a part of this network, the 192.168.1.3. And let's just say this is a /24. So when it needs to talk to other devices within its network, that's easy, right? That PC has an ARP table and it's going to forward traffic to this PC, right? Because it's in its network. Let's say this is 192.168.1.5. So it knows when it needs to forward traffic, hey, that's within my network. I can go ahead and probably just switch that traffic here, right? I don't need to deep dive into this layer 3 header because at layer 2, I know where to switch that traffic, right? With our Ethernet header or our layer 2 header. Now, let's say this PC1 needs to talk to a web server. And that web server in our example is at this IP address, 172.180.9.10. Well, now that PC recognizes that destination IP address right here is outside of its network range, meaning it's not part of my network. So where does it need to send that traffic? Well, now what it's going to do is encapsulate that packet with the default gateway's MAC address, and it's going to send that packet to the default gateway. So during the life of this packet, the only header that's being stripped off from source to destination is this layer 2 header here, okay? This source IP and this destination IP never change in the life of this packet in this very simple network, right? We're not doing that, no VPNs, nothing like that, right? And even if we are, it just gets encapsulated, but that's for another section, right? So this source and destination IP never change. So once this device here, the default gateway, and for our example, that's router 1, gets this packet, it's going to strip this layer 2. It's going to look at that layer 3 header and say, okay, I see that it needs to reach, or it's destined for this IP address. Well, let me see if that's possible, and let me be responsible for forwarding this packet to the destination correctly. So this device is going to reference what we call the routing table or the forwarding database, whatever term you want to use, right? In Cisco, we call it the routing table, okay? The global routing table. It's going to inspect this global routing table, and it's going to have a route this way. So now it's going to forward that destination IP to the next hop. And it's going to replace that layer 2 header with its MAC address of this interface as the source and the destination of this interface. And remember that layer 3 header doesn't change until we reach our destination and it gives a reply back. So in this life of a packet, right, when we need to talk outside of our network, we send it to the default gateway. It strips the layer 2 information, looks at the routing table, decides where it needs to be forwarded at, replaces that Ethernet header, and forwards it on to the next hop. If that routing table does not have a route to that destination IP address or that network, it just is going to discard that traffic, because that layer 3 device right here, that router, that default gateway, is the one responsible for sending that packet towards the destination correctly. Awesome. So now that's really just a high-level overview of a packet, right? So now let's go over the router's purpose. So routers are routing-enabled devices, and we say that because we know multi-layer switches can be routers, are responsible for the quote-unquote life of a packet, right? It needs to get that packet, and when we say packet, we mean our layer 3 header from point A to point B. We're not worried about the transmission control of it. We're just worried about where to properly send this IP. So routers will have locally connected networks that they share with their neighbors. So what do we mean by this? Well, we know we have to build a routing table, right? We have to build that list of known networks. So what do routers do? They share what they know with their neighbors. So all the routers that could be connected to router 1 right here, you can see it. Or this router 2, it's going to say, hey, router 1, I got these networks here. I know about my locally connected networks and maybe anything else that my upstream neighbor advertised, and I want to tell you about it. Or we could look at it from this perspective. Hey, router 2, what networks you got? And now router 2 is going to share and send a routing update. And now when router 1 receives what router 2 knows about, it's going to inspect and say, okay, cool. If I forward traffic this way, I will be able to reach 10.10.10.0/24. Awesome. Now I'm building my table, my little Excel spreadsheet of how to forward traffic. So now my users here are able to talk to users in this network. I'm making that happen for them. So routers enable the global communication of all interconnected computer systems. A fancy way of saying that routers make the internet, right? Without routers sharing and sharing the networks that they know about and forwarding traffic correctly, we wouldn't have the internet, right? You watching these videos at home, that home router that you have right now, it does have its own routing table. It may not be a Cisco router, it may not look the same, but it does. It's going to have something like this. Send all traffic out this way towards my ISP. And then these ISP routers are going to be the hops that get you to your final destination. So let's take a look at that, right? So what I'm going to do right now is bring up a command prompt. And I'm going to do a command called traceRT or traceroute. And I'm going to go direct that trace route to Google DNS servers. So at every hop of the way, this is a router or routing enabled device that's sending my packet along to Google's DNS servers. So at each hop, it's inspecting its routing table and saying, okay, now I need to send, if I'm lag 63, okay, I need to reach Google. This guy's trying to reach Google's DNS. Send that to lag 24. Lag 24 gets in and it says, okay, I need to forward traffic out to 224 or 24.93.64.188 because this packet that I received is trying to reach this destination, and so on. So you can see I'm 10 hops away from Google's DNS servers. Pretty cool, right? All this is possible because of routing and routers. All right, so let's move on. Now let's go into the brain of the router. So how does the router know where to forward traffic? It knows because it's going to build something called the global routing table. So a router is going to store routes it learns from its neighbors into that. And this routing table is going to tell that router how to control traffic, meaning, hey, when you get a packet destined for 22.0.0.8, send it out this way or send it out this way, depending on what that routing table says, right? So the routing table, that global routing table, is part of the control plane, and it's going to determine the best path to send packets. Because as you can see in our diagram here, we have one network here, 22.0.0/24. That's connected to this server farm. This could be anything, guys. Web servers, file servers, LDAP, you name it, right? It's connected to two routers here. One router, or R3, is telling R1 about it via this routing protocol OSPF. R2 is telling R1 about this network via ERGRP. When R1 receives these messages saying, hey, I know about 22.0.0.4/24, it's going to place them into the routing table, and it's going to decide the best path. Is it going to be this way, or is it going to be this way? We're going to find out, right? So we see this, what I call pseudo RIB. RIB is another term for global routing table. It stands for routing information base. So it's deciding to go out gig 1/0 to send traffic to 22.0.0/24. And we're going to see later on in the section why it decided to do that. But this is how that control plane works for a router, right? When sending those packets onto the destination, it decides the best path by doing a lot of calculations about routing protocols, longest prefix. We're going to get into that. So building the routing table. Now let's get into actually building it. So routing tables are built by something called routing protocols. So really a routing table, guys, it's going to have its local and connected networks in there, meaning anything connected to this router, it already knows about, and it's going to place it into that routing table. So how does it learn about other networks, destination networks? Well, it learns about that from its neighbors via routing protocols. So routing tables are built using routing protocols because we don't just want to know about our local and connected networks. We need to learn about the destination, right? How do we forward our traffic? So there are so many different routing protocols that we can use. Static, ERGP, RIP, OSPF are just the ones on the screen here, but that's just a drop on the surface, right? So routing protocols help us build this routing table, and the whole purpose of them, any routing protocol, is to communicate with other routing protocols to build a network of known/destination networks. Whew, that's a tongueful, right? So let's think about it. The whole purpose of ERGRP, RIP, static, or OSPF is to talk to other routing protocol enabled routers to build an entire topology of known networks and subnets. And when we build that, we're able to have full reachability and connectivity between all of our local area networks. We become interconnected. So we have a question here that we're going to answer later. How does R5 forward traffic to this IP address when it knows 4 different ways to get there? And we're going to answer that later. So before we dive into routing protocols, let's go over the control plane and data plane functions of a router. So we already know about the global routing table, sometimes known as the RIB, router information base, or the forwarding database. This is derived from the control plane and essentially just a database of preferred routes a router knows about for destination networks. So as you can see here in our little diagram, little picture, R1 is learning about destination networks via OSPF, and it's going to place that into the routing table. That's all control plane functions, right? All this control plane traffic, this OSPF packets right here, are going to build the routing table. So this is part of our control plane here. OSPF is not a function on this Ethernet interface that's going to actually forward the data, right? It's just able to build that routing table to determine best paths. Now, if we actually look at the data plane, how is traffic actually being forwarded? So in days of old, there's a lot of different ways that a router did this physically at hardware, right? We had packet switching, and then there's another one I can't remember right now, but in modern day, we use something called CEF, or Cisco Express Forwarding. So at the actual ingress and egress interfaces, how is traffic getting forwarded? To switch these packets through a router's interfaces, we have something called the Cisco Express Forwarding Table, which is made up of something called the fib and the adjacency table. The fib stands for forwarding information base. And then the adjacency table is just going to tell us about the next hops, right? Now, this is built from the control plane, so don't get me wrong, right? This is built from our routing protocols. But what this does is allows the fast switching of traffic on the ingress and egress by essentially building that forwarding information base, saying, okay, anything destined to 172.16.00/30, send out gig 0/1. And that's it. That's all that forwarding information base says. Whereas that routing table tells you what routing protocol, it's going to have metrics in here, administrative distance. Nope. In the CEF, this is just how we're switching these packets right now, right? We call that the forwarding information base. And we're going to definitely take a look at that when we get into our lab environments to kind of show you how at hardware, how this traffic is actually getting forwarded. So Cisco Express Forwarding has two tables, right? It has the fib, the forwarding information base, and the adjacency table. The fib table will also have the preferred best path for destination networks, and the adjacency table will have the layer 2 and 3 information of the exit interface and next hop ready to forward traffic. So if you look at this one right here, I just pulled this from Google, right? If we have a packet that's destined for 10.11.100, boom, it's going out that next hop right away. It knows exactly where it's sending it. It has that interface and that IP address information. This looks a little different from our routing table because, again, we're missing all that information about routing protocols, the metric, where it learned it from. No, the CEF table, we just want to know where we're sending this right now. We want to know the prefix that we know about or where to send. We want to know the next hop and that exit interface or that egress interface. So this enables the quick switching of packets within our router, right? And this is going to be done at hardware. So this kind of depends on the iOS, but you can see here that at that data plane, right, at the actual interfaces, we'll have ASICs that switch quickly. Now, if you go ahead and do a quick Google search, and type in the CEF use CPU, you're going to see on Google some that say yes and no, and it really just depends on the iOS, right? Because that forwarding information base is still built from what we learned on that global routing table. This is just a quick way to get our packets switched through our router. Okay, so I'm going to go ahead and pause or stop this video. And then in our next video, we're going to start deep diving or high level overview of our routing protocols.